This will be on the derivative of the inverse function. I'm assuming that the function is defined on a closed interval, and when I write f prime of x, I mean the appropriate left or right derivative if x is one of the endpoints. Now, if I assume that the function is defined on an open interval, then of course when we discuss the derivative, we would mean the two-sided derivative. All right, so here's the theorem. If you have f taking the closed interval to R be continuous and 1 to 1, and if the derivative exists for some x and it's not 0, then the derivative of the inverse function at f of x exists, and it's given by this formula. So I want to show why that is. All right. Since f is 1 to 1 and continuous, it follows that f inverse is also continuous. This was proved earlier in the section on in the chapter on continuous functions. And it also follows from what was done there that the function f is either strictly increasing or strictly decreasing. So I have here that f of this interval is going to be some closed interval. Now, in all the argument that follows, I will constrain h to have the appropriate sign if f of x is at an endpoint of this closed interval. Otherwise, it could have either sign, and you would just need to have the absolute value of h small enough. Okay, so we'll be at a point where f prime of x is not 0 and f of x equals to y. Then from definition of inverse function, h is equal to this minus this, because when you look at this, it just gives you y plus h. When you look at this, it just gives you y. So yes, that's equal to h. Now, by differentiability of this function at f inverse of y, which remember is x, I have that this is equal to f prime of x, that's the derivative of f at f inverse of y, times this thing minus this thing. See, there it is. Plus little o of this difference. Now, by continuity of the inverse function, eventually, if I let h be small enough, the absolute value of little o of this expression will be less than 1/2 of the absolute value of f prime of x times the absolute value of this thing. Okay? So if I look up here and I use the triangle inequality, I can say that the absolute value of h is bigger than or equal to absolute value of this thing minus 1/2 of this. And you see this thing minus this thing is equal to this. So now if I look at little o of this difference divided by absolute h, that is smaller than or equal to this expression. What did I do? I substituted this thing for the h. And this thing is smaller than the h, so the expression got bigger. Now simplifying, that gives me this. So that shows me that little o of this difference is little o of h. I want to go over why that is. It's because by continuity of the inverse function, if I take a limit as h goes to 0 of this, I get 0. So if h is small enough, I could say epsilon is bigger than this thing, and that's bigger than that. Since epsilon is arbitrary, this satisfies the criteria needed to say that this expression is little o of h. Okay? So wherever I see this, I can put this. So now I go back to star up here. Okay? And from that, I can say that h is equal to f prime of x times this plus little o of h. Now you see the little o of h here took the place of this here. See? So now if I just solve for this expression, it equals to 1 over f prime of x times h plus little o of h. And now this, remember what y was? Y was f of x. So I get this expression here. And that is exactly what it means to say that the derivative of f inverse exists at the point f of x and equals 1 over f prime of x. So that proves the theorem. Now this is real easy to remember if you don't worry about the mathematical issues. All you do is you write f inverse of f of x equal to x. Now use the chain rule. Just pretend everything's differentiable. It will be. That's essentially what we just showed. And we can then write f inverse prime of f of x times f prime of x is 1. Divide both sides by this because it's not 0, and then you get this formula. So this is very easy to use, to remember. And some of us like to remember it in terms of these formal symbol manipulation ideas because they're easy to work with. Okay, look at this one. If you were to take the derivative of f of x, it would be this. And this expression is always positive. Now, I'll leave you to determine that, but it's real easy to see that that's the case just using the quadratic formula. It has no real roots. So it has to either be always positive or always negative. And it certainly is positive for large values of x. So yes, this will always be bigger than 0. So the function, this function, is strictly increasing. Now, since it's continuous, I know its inverse is continuous. And from what well, let's go over why that is again. Since the derivative is bigger than 0, I can use the mean value theorem and write this. And I know this is positive and this is positive. So if x is less than y, this would be positive and this would be bigger than that. Okay, now I have no way of solving this expression for x. I don't know how to do it. But I can see that f of 0 is equal to 8. And so by this that I just showed, the derivative of the inverse function at 8 is equal to this, and that's 1 over f prime of 0. Well, f prime of 0 is just 7, so this is 1/7. Okay? Now, a lot of times we push symbols like the following. We have f of x equal to y, and the inverse then would be x equal to f inverse of y. I take dx by dy, that's f inverse prime of y. That's 1 over f prime of x. That's 1 over f prime of f inverse of x, because, see, the x is f inverse of y. And that's the same thing we had earlier. So that's how the derivative of the inverse function exists. And we'll stop here.